The next thing I wanted to look at then with you is ICs, integrated circuits. And it just means it's what it says in the tin. You get smaller circuits, add them together to get a bigger, more comprehensive set of abilities within the one chip. We've all used the 7805 voltage regulator, just a 3-pin device. Your voltage comes in, you put the common down to 0 volts, and the output is 5 volts. So you can put in 15 volts in the way in, you get 5 volts out. You put 12 volts in the way in, you get 5 volts out still. But inside that, even something as simple as that, it's got 39 components in it. A whole bunch of transistors and resistors and so on, Zener diodes. There's a whole bunch of material goes into that one little case that you're seeing at the end there. Now that's only the tip of the iceberg, but just to show you that something I use every day in building modules. It appears in almost everything because all our kits are designed to run on 12 volts because 12 volts is what you're going to find around your layout. But most electronic circuits work on the basis of 5 volts. Right. Now take that into a much larger scale than the general voltage regulator. That's a circuit diagram from a magazine for an audio amplifier, old style. I didn't even do a component count because life's too short, but there's its equivalent for a 5-watt amplifier. A handful of parts does the exact same thing nowadays. We've managed to package all of that complexity into one little chip. A little, what, 10-pin chip. And that's, again, only the start of it. That's another logic board that's used for some control purpose. And you can see there's loads and loads of individual logic gates and so on in there. Lots of inputs, lots of outputs. And any change that has to take place there has to be a whole new board, because if you've made a mistake in design, you have to start again. That can all be replaced now by PIC chips or Arduino chips doing a very similar function. More of that a bit later. There are some interesting facts about just how far we have progressed. The GTX 1660, that's the video card that I'm using on my desktop right now, has got 6.6 billion transistors in it. I mean, it's mind-boggling. The GeForce 1080 has got 12 billion transistors in the one. And the Xbox, even the little Xbox one, 5 billion. Your iPhone, billions. And they're all inside a chip about the size of a postage stamp, or maybe, depending on which one, maybe a bit larger. If you try to do that same video card using discrete components, you would need a printed circuit board the size of Bristol or something, and or 50 football pitches just to accommodate all the wiring. And yet they've managed to get all that down by integrating it into one chip. It's amazing and we're just started on that route. And we use these in model railways as well as other general electronics. I thought it was making a point about the difference between ICs and PICs and Arduinos. You'll see a list there of a selection of the things that you can use ICs for. You'll find them in a whole range of devices in the home. Your toaster, your washing machine, and so on and so on. Now, an IC in general just means integrated circuit. Lots of components in the one board. But in practice, what it generally means is there's a device dedicated to one job. Like the 7805 at the top of the list, it's just a voltage regulator. That's all it does. You can't make it be an audio amplifier, you can't make it do anything, relay switching. All it does is takes an input voltage, gives you an output voltage. It's got one job to do, as is a lot of these as well. We'll look at some a bit later, but they're all dedicated to one particular activity. Sometimes you can change a component externally here or there to tweak it a bit. But at the end of the day, it does one job. So we can do trimming around the edges with some components to get a slightly different effect. End of the day, they're dedicated to one job. They're pre-programmed inside to do that, hardwired inside. PICs and Arduinos, microcontrollers in general, are programmable. That's the difference. You can decide what they do. They can't do some of the jobs I've just listed here. They can't act as a voltage regulator, right? Really, right? For example. But you can write a program to say that pin that's coming in this instance, goes to a pot. That output there, in this instance, goes to a relay. And the next time I program that same chip, that input's coming from an LDR and the output's going to a LED. So you can decide, and the logic in between, if that switch goes, what happens on the outside here? If I change the values here, what happens to the values there? You're in control of that by changing what's inside the chip. So you have much more control with PICs and Arduinos. Downside is, of course, you have to learn a bit of programming to do it. So most people stick with dedicated ICs to do a particular range of jobs. And along that way, I'll look at a few of these along the way. So that's the difference between ICs and programmable microcontrollers. What are examples of these then? The most common initially were logic chips, where you can have permutations that have to be sought before you get an output. For example, at the top, we've got two push buttons, a battery and a lamp. You have to push both buttons down at the same time to light the lamp. It's obvious. If you press button A on its own, nothing happens. If you press button B, nothing happens. You have to press both. And to the side, it's what we call truth tables, which shows you what happens, what to expect from that circuit. So if that was inside a black box, that would tell you what happens. But we can see it happening here. It's called an AND gate for an obvious reason. You have to push that and that. Both of them have to be down before anything happens. In other words, that switch has to be closed and the other one closed before the light lights up. Or it says there 1 and 1 gives you a 1. That's the truth table. The second example has got two push buttons, but they're in parallel. In this case, any one of them will bring the light on. They're called OR gates, OR logic, because one or the other. And you'll see here that when both switches are unpressed, nothing happens. Press any one of the two buttons, or both, doesn't matter. Any one or both, then what will happen is the light comes on. And again, you'll see a different truth table at the end. 2 zeros gives you 0, but any of the other ones will give you an output. So that became the building block for many circuits initially. I remember building a model railway in my previous house based on a ZX81 little computer and lots of combination logic chips. What a nightmare. We won't go into that one. So we can use this to achieve results on the model railway We can use that technique of ands and ors within programming for programming chips. The symbols, unfortunately, depends whereabouts you are. There's more than one way to describe AND gates and OR gates and so on. Just got to live with that. You can look these up anytime. There's an example I got out of a newspaper. Have a quick look at it for a minute and see whether you think, if I was to do that using logic gates, would that be an AND or an OR that would achieve the result I want? There's keywords in there that tell us. And that has to happen, and that has to happen. So it only does what it's meant to do if you meet both conditions, that and that. So if we were to use Apple's technology using a simple logic gate, it would be an AND gate. And we'd have two sensors. One is a car moving, two is a person on the phone. And if they meet both conditions, then we're going to block the texting, so they can't break the law. So that's an AND gate in practice. We want to implement it. There's another one. Now, again, the clues in the words.
Yeah.
Each stall has got a sensor. So any one person leaving any one stall will start the alarm going. It doesn't wait till all 6 people are finished doing their business and come out. Anyone opening the door will start the process. So again, that would be solved using an OR gate. Door A or door B or door C or door D, any of those doors open will ring the alarm. So you can solve a problem by thinking about it first, describing it, and that decides what approach you have for logic gates. Practical example of it. We've got a station there, and the station's got 2 tracks, and it's got 2 totties. And what we want to happen is that when the train comes into any one of those totties, the light comes on in the station. Alternatively, I've got a switch here that at any point in time I can bring the light on manually. So I want it to be operated either when that happens, or that happens, or that happens. Any one of these 3 will do the job. Right, so that button simulates the totty. Train comes into that siding and light comes on. Train comes into that siding, light comes on. Or if I want to manually control it, wrong side. So I'm using that chip in the middle to allow me 3 different ways of controlling the light for that station. I used that particular chip to do it, and I only had to use one of them. It's got 3 lots inside. Only use one of those. And there's the truth table for it on the right hand side. So now that's something you can implement anywhere you like in your layout. Put a couple of totties, put it into that logic chip, and then feed that logic chip to the lights on your station. And it's automatic lighting when the train comes in, no matter which siding you're on, or whether you want to have manual control. So that's an example of using logic. This is a simple logic gate that costs 20p or something, to automate a small part of your layout. tell you, like, it costs 43 pence. Yeah, I was exaggerating. It costs 43 pence to do it. So there's logic gates. Here's another one. One of the members, in fact, I think it was you, Craig, was talking about running lights. And running lights, we've got our own random lights. We've got our own flashing lights. We don't have a kit for doing running lights, which is essentially just that. There's a little pot here, a trimmer here, that we can adjust the speed at which they flash through 10 different LEDs. It's made up of 2 parts. You'll see a small chip on the right-hand side there with 8 pins on it, away at the end here. And all it's doing is sending out pulses. It's a timer, just sending out pulses. And then the chip is up here, receives those pulses, and every pulse coming in makes it switch from one light to the other. It's a 555 timer that we'll be looking at a bit later. And this is a decade counter that we'll look at now. So it's only two components really. Decade counter just means that every time you get a pulse coming in on pin 14, you'll see it says clock there. Every positive pulse will make it switch from one pin to the other, to the other, to the other. At any one time, only one pin of these blue ones is actually active. And which one it is depends as you clock it round. It's also got a reset. If you take it high, then the count starts all over again, even if you're not finished doing all 10. Again, only costs a small amount of money. You're talking about pennies. And that's how it works. You put an input here to go high, and every time it goes high, it moves from one pin to the other, 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 till it gets to the end and starts all over again. Unfortunately, the pin layout, you would think that the pins would go from pin 1, pin 2, pin 3, pin 4, but in actual fact it clocks 3, then 2, then 4, then 7, then 10. I don't know why they designed it that way, but that's how it works. And I've got one here. There's a 4017, and there's a bunch of LEDs around it. And what I've done is I've just got at this stage just a push button. And every time I push the push button, we cycle around different ones. And the faster I click it, the more quickly. So we can manually switch from place to place to place to place if we wanted to. Or in the case of the runner, we can feed that with a timer that's pulsing. Another option, if I can find it, there we go. If you don't mind it being a fixed speed, what I've put in, instead of the switching it, I've put in a flashing LED. And every time the LED flashes, it moves a 407 one more pin round. So if you buy a flashing LED and a 4017, you've got yourself a running light. If you want to have control of the speed, you'd have to have something coming in here that you can change the rate at which it switches. That's what you're looking at there, 4017, using a push button, using a LED. And that's what's happening. Every time you pulse it high, you switch the previous one off and the new one on. So it works its way around. If you want to have an even greater running lead, you'll notice there that there's a carry. So when it gets to 10, that changes state. And you can feed that into another 4017. All of a sudden, you've now got a running lead of 20 leads, or 30 or 40, whatever you want. You can use that facility. You can also use it as a frequency divider. Let me just unplug this a sec. Right. Because, as I said earlier, it's got a reset. On its own, it would normally clock through pin 3, pin 2, 4, 7, all the way along. But in this case, I've got pin 10, you'll notice, connected to the reset. So it'll activate pins 3, 2, 4, 7. When it gets to 10, it resets and starts all over again. So we can use that so that every time we get to pin 7 or 10, we can divide the input up depending on how many steps we get before it resets. So we can turn it into a frequency divider as well. Now, what I've got there, the bottom half, you've seen the top half already. The bottom half is just using a 555 to generate pulses. And this time, it's going to the same decade counter. We're not using all of them, we're only using 4 of them. And those 4 are going to drive my stepper motor driver. So let's see if we can get it working. There we go. So the 555 up here is driving the 4017. We're all using 4 of the outputs before it resets, that is, and then they're going into the stepper motor. Only goes in one direction. But you can control the stepper motor without having to have anything other than a 99p driver and a 4017 and a 555. There's also 7-segment displays. You've all used these, you've all seen them on lots of home equipment. And every segment has got its own letter, its own segment, and every segment has to be lit individually compared to the common. It's a bit of a pig to drive them, so they actually bring out a driver to do it. Another logic chip, and all it does is, we're all happy now with the idea of the BCD coming in. If I had used that same BCD switch I showed you earlier and fed one of these into here, as I pushed those buttons, you would see number 7 on here, but you'd also see number 7 over there. A much bigger display. Or if you're using it and you're feeding the BC and Ds from other electronic equipment, you're able to then get a digital readout from it. So it's become a bit old hat compared to OLEDs and LCD screens and so on. But again, needs no programming to achieve that effect. And that's all that does. It just converts BCD to 7-segment. You can't make the 7447 do anything other than that. But what it does is good at. Right. Now, a lot of the stuff we do in model railways revolves around drivers. We want to be able to have a TOTI driver motor, driver relay, driver high power lead or whatever. And what it's doing is it's taking, like I said earlier, a low current in to be able to switch a much higher current out. And they come in two flavors, as you see there, multiple drivers and more specialist ones. Let's look at the multiple one. There. Looks like that. It's a 16-pin chip. That's one of them, at least. It's got 7 inputs. It's got 7 outputs. You change the state of pin 1, that will change the state of pin 16. You change the state of pin 5, that will change the state of pin 12. What's inside it? Well, that's on that side. I've got a question mark there just to remind you that that symbol means an inverter. So if you put a high voltage into pin 1, you get a low voltage out. You put a low voltage in there, you get a high voltage out. You get the reverse of what you put in, albeit a much higher current. So you invert the voltage, but you increase its current carrying capacity. So that's what that question mark's about. The other question mark shows that inside that chip, there's a bunch of diodes. And what they're there for is for reverse voltage, back EMF. If they're using this to drive a motor, one of these outputs, you're using it to drive a relay or whatever, and it's inductive, then when you switch the current off, you're going to get a back voltage which could damage inside the chip. And these diodes are there to shunt that away. The exact same as you see when you've got diodes across a relay externally, which is very common. These are built in to save you the bother. There's its description. We call them suppression diodes. And each channel can handle a half an amp on its own and slightly more just for a short time as a peak. They're high current Darlington arrays. Remember I mentioned earlier about how you'd have 2 different transistors, one a small driver to drive an even bigger driver. That's what the Darlingtons are doing there. And they're high voltage, so we can use these to drive quite a range of stuff. What's an example of that? Well, there's the traffic lights kit. The traffic lights kit has got 6 different LEDs to give you 2 sets of lights, or you might want to have 4 actual sets because 2 are common and 2 are common, so you'd have effectively a dozen different LEDs. And depending, if we were able to want to drive them at full pelt, in other words, you know, if a LED is capable of being driven at 20 milliamps and you drive it at 20 milliamps by your choice of dropper, then you could overload the PIC itself, can't handle that amount of current. Or some members said, I want to have an O-gauge layout or garden layout, and I want these lights to be much brighter. I don't want a LED, I want it to be an actual large LED or a filament, large filament. In which case, in between the PIC and the LEDs themselves, or the lights themselves, we can have a high current driver. So although this PIC, that pin or any of those pins can only have a maximum possibility of 25 milliamps each, once it's been through the driver, it's capable of doing 500 milliamps each. So this meant that this kit could handle ordinary LEDs or high power lights, depending on what your uses were. So that's an example of using an array of drivers, multiple drivers in the one chip. Moving on. That's what it looks like, sorry, that's what it looks like. There's your PIC, and next to it we've got the driver set. Now, here's a dedicated driver. We use it a lot. We've got that inside the exhibition layouts that we use. And what it does is it's two drivers in one. You'll see the left-hand side is kind of grayed out because that's only a duplicate of what's on the right-hand side. In effect, you could run two different motors, or you could actually run a stepper motor and so on if you wanted to with this. But looking at an ordinary motor, what we have is the voltage you want to drive is separate from the logic. The logic, as always, is plus 5 volts for the actual logic inside the chip, like most chips are. But your motor might be a 12-volt motor, might be a 9-volt motor. So what you have to do is you have a separate pin that you connect the voltage that you want to drive this motor at. And once that's set up, it's quite simple. You've got a couple of pins. One's called the enable, and the other are the direction pins. So you take your two leads from here to the motor. The two green ones, in fact, go down to here. If the pin's in the middle, nothing happens. If you bring down the top one here to 0 volts, the motor will start spinning clockwise. If you bring that one down to 0, it will start spinning anti-clockwise. If you brought them both down to 0, nothing happens. You have to have one high and one low to go in one direction. If they're both high, nothing happens. If they're both low, nothing happens. If one's high and one's low, it works, and vice versa. And we can show you that here. See, normally around a table looking at this and trying it, but we can't do that here. Right, what's the best way to show it? Right, there we have. I've got a motor. It's getting fed from this 293D. I've got two buttons. If I press one button, it goes in one direction. If I press the other button, it goes the other direction. If I press both buttons, nothing happens. If I don't press any button, nothing happens. You have to have one high and one low. And depending on which one's high, depends on the direction. And it can handle high current. Not only that, you can either do it manually, like I've got there, with buttons, or that could be fed, in our case, from a PIC chip. So in place of where I've got the switch saying clockwise and anti-clockwise, I can have these two inputs from a microcontroller. And I can control traction now from a microcontroller. I can make a local go back and forward, up and down the track. You can make it stop. I can make it reverse, make it stop again, simply by using two pins only. If you want even a higher current motor, all you do is you can parallel the two inputs and the two outputs to get even more current. So the 293D can operate one motor, like I'm showing you here, can operate two motors independently, can operate a high power motor if you parallel the two inputs and the two outputs, or you can drive two coils of a stepper motor using this. So it's very versatile, and again, it's not a particularly expensive part, and you can use that in conjunction with an ordinary switch or any microcontroller. Next thing then to look at is our comparators. And I want to work through how this DCC detector works. Yeah, simply from the point of view, it shows you how a comparator works, but more interestingly, I think, is the basic electronics course we looked at what different components were and what they did, and what components look like on a schematic diagram. This time I want to show how this works stage by stage. So the first thing is it uses this chip called a comparator. In fact, there's two in the one case. take the one on the left, for example. It's got two inputs called plus and minus. And what we're going to do, and one output, of course, what we're going to do is we're going to put a fixed voltage on one of those pins and then measure what comes in on the other pin. And when the pin reaches and exceeds the other one, which is called the threshold, then the output changes. There it's there. So what I've done there is I've put in an 8K2 and a 3K9. So if I put a 12 volts across that chip, then approximately that's close to 8 and 4, which would give you, a third of the voltage at that point. So roughly 4 volts is coming in here. And that light won't come on now until pin 3 reaches at least this 4 volts. Anything below that, nothing happens. We can use that as a switching point. And it switches, unlike the LDR totty, this switches instantly, either reaches it or it doesn't. And I've built this one just to show you. I've got there's the variable resistor. And if I turn it, right, so you get a nice clean switch on when you get to a certain point there. And in this case, it's roughly 4 volts. Yep. And that's just a bit of Vera board with that exact same circuit on it, just to demonstrate how a comparator works. On the LDR, on the DCC totty, we use both of them. I've only got one here, but it's used both. Let's have a look and see. There's the schematic of the DCC totty. Now, some of you will already know how to read a circuit diagram, but let's just do it from scratch. The comparator is called an LM393, and it needs, like any other chip, it needs a voltage supply. Where's it getting it from? Well, it's taking the supply from the DCC itself, from the track. There it is in red. And all that's happening is that the DCC, as you know, is bipolar. It's high 1 minute, low next minute, high, positive, negative, keep switching. So this will filter off 1/2 of the cycle, charge a capacitor, and that becomes a stable power supply, which then feeds the chip. So there's the voltage going here to power it, and the other end is the 0 volts. So we've now been able to power up that chip just from the DCC. And that's what these components do. So now we know that, we can take it out of the circuit. We only need them to show how we got the power. That's what you're left with. Now, how do we detect DCC? Well, we've put two diodes, two fast-acting Schottky diodes across, in series with the supply. The DCC comes in, has to go through these diodes and back out to the track. Now, we mentioned earlier that diodes have got a voltage drop across them. And that voltage drop is regardless of how much current it's passing. So I could feed this to a 90 milliamp N gauge local or a 2 amp O gauge local. It would still drop the same voltage across the diode. So because the DC is constantly changing polarity, 1/2 allows the current to flow directly through as if nothing's happening. The other one will trap the voltage across here and develop a voltage. But only if there's current flowing. In other words, we only get a voltage dropped across here if in fact there's a loco on that bit of track. Whether it's stationary or whether it's moving, doesn't matter. If that's on that bit of track, you get sufficient current flowing through here to develop a voltage and that feeds in there to the comparator. What's it comparing it with? With 0. In other words, anything above 0 will trigger that output. Anything above 0 triggers it. So if there's no local in here, they're both at 0. The minute some train goes in there of any description, that's going to rise sufficient to switch the output. So now this pin here, pin 1, knows when there's a loco there. Having said that, what's coming out are pulses that are always high. So what's happening looks like that. When that's active, there are pulses coming across here, being developed across this resistor. We don't want pulses, we want something smooth. So we feed that through the diode here, like that. The pulses here come through the diode and eventually charge up that capacitor to the point where the voltage across here is sufficient to switch the other output on. But it's smooth now. So instead of getting pulses, the second comparator gives us a smooth fixed change. And the fixed change is then used into an octal isolator. Now, Keith, next Sunday is one of the talks will be how to use an octal isolator. So we'll cover that in a bit more detail. But now the input here has changed the output there. And as long as the train's in the section, then that's going to be a steady, unchanging output, which can then be fed to, well, whatever. So that larger circuit boils down to discrete bits, one to achieve power for the chip, one to detect that there's a train on the track, one to convert the pulses into a smooth output, and then finally the output itself. So there's 4 stages, and all you need to do is don't look at this thing in the round, look at what does each component do in stages. And all of a sudden it's not as complex as it looked first. There it is in practice. We've used the octal isolator to feed straight into a servo 4 to operate points. Or we can put it into a relay via a good old friend, the driver. Transistor driver to switch a relay. Trains comes into the section, the relay operates. There we are, simple as that. Nothing to it. So that's a comparator, and we can use that to detect voltage levels that are derived from, for example, light levels, stuff like that. Here's another example of a completely dedicated chip. It can do nothing other than what it's designed to do. We've sold loads of these to members. It's the wee key fob, you know, and its associated receiver. And this key fob has got four buttons, as you can see there, and each button then will send out a unique code. It's going to transmit eventually into the real world. But what it transmits will be a sequence of highs and lows that are determined by what button you've pressed. So press button 1 will give one set of codes out, pressing button 3 a different set of codes, and so on. And if you haven't seen it working, each button press will bring on a different LED. So it transmits a code that's built into it, predetermined. And the other side, we have to convert that code back to 4 different outputs. So that little module there is a decoder. Unplugs from that. That's what you buy. Its job, that chip's job, is to decode the signal that's coming in and put out on those pins the appropriate change of state. And you'll see that up there. There are 4 outputs. And there's some other features if you wanted it, but essentially it's doing 4 outputs. And that's all it does. So one chip takes an input and outputs a sequence. This chip here takes a sequence and results in 4 different outputs. And that's all they can do. They're not programmable in any other way.